All right, let's look at this problem called next greater element. So essentially, in this problem, what we are given is we're given an array, and we have to find for every element what is the next greater element. What does that mean? Well, let's look at this example. So in this example, 1, 2, 3, and 4. So we have to find for every index for 1, for this, and this, which is the next greater element. So for 1, who is the next greater element? Which immediately to its right, which element, which is the first element, which is bigger than 1. Well, so for 1, the answer is 3, right? For 3, the answer is 2. For 2, the answer is 4. I'm sorry. So for 1, the answer is 3. For 3, the answer is 4. For 2, the answer is 4. For 4, there isn't an accelerator, so it returns minus 1. Look at this another example, 68013. Let's look at it on a whiteboard. So the example input is 68013, right? So what is the next greater element for 6? Well, it's 8, right? What is the next greater element for 8? I can't find it. For 0, it will be this one. For this one, it will be this 3. For 3, there isn't one, so minus 1. So how can we solve this problem? So essentially, if we talk about brute force is quite easy, right? This is brute force is exactly what we're doing, which is we are at this index, so we look at the entire array to the right of it, and we find the first. So we go from left to right, and we find the first guy which is greater than this, and there the time complexity would be n square. How can we do better than n square? Well, the way to do problems like this, where next greater or next smaller or next greater on the left or next greater on the right, is to use the concept of monotonic stack. So what is this? So let's talk about the approach first. So basically what we'll do is we'll keep on adding all elements into the stack, okay, to go from left to right. So I add the first element 6 into the stack, right? The elements that are in the stack are all the elements for which I'm yet to find my next greater element. So for 6, I've only seen 6 so far. So I don't know what its next greater is. Now I'll look at the next guy. Next guy is 8. So before inserting the next guy into the stack, I will first check, hey, are there elements on the stack for which can I be the next greater element? So when I look at a 6, 6 is less than 8. So yes, so if that is the case, so as soon till I find the elements for which 8 can satisfy, 8 can be the next greater element, I'll keep on removing them from the stack. So I'll remove 6 from the stack. I'll say for 6, the next greater element is 8. And now the stack is empty. I insert 8. And then I look at the next guy. Next guy is 0. Again, I first check the stack. So basically what I'm checking it in the stack, I'm checking the stack if in the stack there is somebody who is smaller than me. 8, well, 0 for 0, 8 is not smaller. So 0 cannot be an extra element for 8. So you just add 0 into the stack. Then you get 1. Now when you look at 1, again you do the same thing and you find there is something smaller than 1 in the stack. So you remove that guy and 1 will be the next element for 0. And for 8, 1 can't satisfy the condition, so 8 remains. And now you add 1 into the stack. And now after that, you get to 3. Again, you look at the same thing into the stack. You see 3 can be the next element for 1, but it cannot be for 8. So you insert 3 into the stack. So you're done. At the end, whatever elements are left in the stack, those are the elements which for which you could not find the next letter element. So you can say for 3, I could not find the next letter element. For 8, I could not find the next letter element. So now, what is the meaning of monotonic? Well, the monotonic meaning is it's either non-increasing or non-decreasing, like one of those things. So in this case, the stack that we are building, at any point when we insert an element into the stack, we ensure that there is no smaller element, sorry, no, yeah, correct, no smaller element into the stack. So when the stack is building from bottom to top, if you look at the stack from the bottom to top, we are always adding a smaller element, never a greater element. Because if the greater element we are adding, then then that element is an extra element of myself. Then I don't need to the stack, so I'll remove myself. That's another idea. Now, if you think about the time complexity of it. What really we are doing is for every element, we might be inserting it once into the stack and we might be removing it once from the stack. So the overall time complexity is 2n, which is nothing but n. Let's take another example maybe to understand the problem slightly better. Let's take a very typical edge cases, right? So let's look at first this case, 1, 2, 3, 4, 5, right? And this is the case, how will the stack build? So we'll put 1 into the stack, then we look at 2, we'll say 2 can satisfy the condition for being the next element of 1, so 1 will be removed and 2 will be added. Then again 3, Well, for again, when you add 3, 2 is smaller, so you'll remove it, and I'll say two, next element for 2 is 3, and you'll add 3 into the stack. Then you look at 4, you look at the stack, you'll see a stack has something smaller, so till stack is something smaller, I will be the next the element for that. Then we will have added 4. Alright, and after that, now we look at 5. Again, so 4 next data element will be 5, and I'll be left with 5 in the stack. And so now 5 is empty, right? That's done. Now look at another example, completely reverse. 5, 4, 3, 2, 1. Right? So what will happen in this case? Well, in this case, you'll add 5 into the stack. Then you'll add 4. 4 can be the next element for anything in the stack. That's the beauty of it. Like if 4 cannot be the next element for the top guy, then all the other guys in the stack are actually greater than 5. So they can, 4 can definitely be the because the stack is, if you go from top to bottom, stack is decreasing. And if you go from bottom to top, the stack is increasing. And I'm not considering the equal case, but you get the sense of it, right? So that's why you only have to check the top. You don't have to check anything below 5 to know whether or not the stack, whether or not 4 can be the natural element. So after 5, you add 4, then again 3, then again 2, then again 1, and you cannot find the next element for any of them. Right? These are the two extreme cases. In both cases, you just went through the stack from left to right. So let's implement this in code now. So basically, we use a stack. Uh, stack equals to new stack. Then you go from int I equals to 0, I is less than array dot length, I plus plus, and let's add this long, let's call it result equals to new long of array dot length. So for every element, what are we doing? Well, till my stack is not empty and the top element of the stack, so and we are saving the indexes in the stack, not the actual value. So we'll do array stack dot peak. So the top element, if I am the next element of the top guy, so that means I, who is array of I, if I am greater than this, till this happens, I will set result of stack. Then for that guy, I will remove it from the stack and I'll set myself as an etc element. And at the end, I will add myself in the stack. And now whoever is left in the stack at the end of this iteration are the ones for which next element could not be found. We can do another loop, or we could just initialize the array with -1 here. So all the elements which are left will remain -1, and we can just return a result like that. We submit this code. So it's a typical concept called monotonic stack that's got used in various problems to improve the time complexity by adding an extra space complexity. All right.